The nitrogen in amines is usually sp3 hybridized, but if bonded to an sp2 carbon, it assumes a partial sp2 character. The amines can have a variety of structures due to the ability of the nitrogen to bond 1, 2, 3, or even 4 carbons. Thus, we can classify amines based on the number of carbons bonded to the nitrogen. We say a primary amine if there is 1 carbon bonded to the nitrogen, secondary amine if there are 2 carbons, tertiary amines if there are 3 carbons bonded to the nitrogen, and quaternary amines if there are 4. In quaternary amines, the nitrogen carries a positive charge, such as this one. If the groups of a tertiary amine are all different, the amine will be chiral, but resolution is usually not possible due to rapid interconversion. Here, the energy needed to interconvert a chiral tertiary amine is not very high, that at room temperature, this interconversion occurs very rapidly. On the other hand, chiral quaternary ammonium salts can be resolved into enantiomers. Here, the interconversion is no longer possible, and so you can have mirror images of 2 quaternary ammonium salts. Special techniques can separate these 2 types of compounds. Many amines have common names. Usually, we identify all alkyl substituents to the nitrogen alphabetically and end with amine. For example, in this case, the nitrogen is attached to a secondary butyl group. Thus, we call this sec-butylamine. In IUPAC, you replace the E of the corresponding parent alkane with amine. Thus, in this case, you need to identify the parent alkane. Here, the parent is butane, and the amino group is attached at the 2 position. Thus, our name is 2-butanamine. Now, in here, the common name uses alphabetical ordering. So, this group attached to the nitrogen is ethyl. The other side is propyl. The name of this compound is ethyl propylamine. For IUPAC, we consider the smaller group in the amine as a substituent, and the longer group is the parent. The longer group in this case carries 3 carbons, so we name it as propanamine, and the ethyl group is a substituent to propanamine. Since it is attached to the nitrogen, we give it a locant N. So the name of this compound in IUPAC is N-ethyl 1-propanamine. The substituent NH2 is called the amino group. For this compound, the amino group is taken as a substituent to 2-butanone. So here the name is 4-amino-2-butanone. Primary, secondary, and tertiary amines exhibit hydrogen bonding with water, as the nitrogen in amine can interact with the hydrogen of water. Also, the hydrogen attached to the nitrogen can interact with oxygen in water to form hydrogen bonds as well. Thus, low molecular weight amines tend to be water-soluble, whether they are primary, secondary, or tertiary. However, large molecules containing amines are often insoluble in water. Tertiary amines cannot form hydrogen bonds to each other. As a result, their boiling points and melting points are low. Nitrogen forms a weaker hydrogen bond compared to oxygen. As a result, amines have lower boiling points than the corresponding alcohols. More substitution on nitrogen reduces boiling points. Considering this compound with 4 carbons, and is compound also with 4 carbons, the alcohol has higher boiling point than the amine. As the number of substitution of the amine increases, the boiling point decreases. This is because of the decreasing tendency for hydrogen bonding. Primary alkyl amines are more basic than ammonia. The alkyl groups stabilize the aminium ion. Going back to the acid-base reaction and starting first with the protonated amine, the reaction in this case involves the formation of the amine from the aminium ion. Take note that if this is an alkyl group, the alkyl group is an electron donating group, and it can stabilize this positively charged nitrogen. Thus, the aminium ion becomes more stable, and so this compound becomes more basic. Basicity is the tendency of a compound to accept a proton. If the aminium ion is stable, then this compound will accept a proton more easily. If we compare a primary alkyl amine to ammonia, ammonia does not have an electron donating group. It is less basic because its ammonium ion cannot be stabilized properly. So, when we consider pKa values, methylamine or methanamine is more basic. That is, its conjugate acid has a higher pKa compared to ammonia. The pKa values are relatively similar for many primary alkyl amines. Now, it is reasonable to think that if you have 2 alkyl groups attached to the nitrogen, then this aminium ion will become more stable. Thus, you would expect that this amine will become more basic if it's secondary. Thus, in a general sense, in gas phase, the tertiary alkyl amine is the most basic, followed by the secondary, then the primary, and then the ammonia. Nevertheless, in aqueous solution, the order of basicity is not the same. The reason for this is that the tertiary aminium ion is poorly solvated. Upon protonation of the tertiary alkyl amine, the hydrogen bonding is relatively diminished compared to primary and secondary alkyl amines. Thus, its basicity will decrease. Aryl amines are weaker bases than alkyl amines. Its pKa value is only 4.58 compared to the pKa value of methanamine. The reason for this is the availability of the lone pair. The lone pair is responsible for the basicity of the nitrogen. In aryl amines, this lone pair is interacting with the ring through electron delocalization, thus is less available for binding to hydrogen in an acid-base reaction. Thus, the pKa of aryl amines are very low. Similarly, amides are much less basic than amines. The reason again is that this lone pair of the nitrogen is involved in resonance structures, especially here that oxygen is electronegative and pulls electrons towards itself, including the lone pairs of the nitrogen. In general, amides are much less basic than aryl amines. Amines insoluble in water will often dissolve in dilute aqueous acid as an aminium salt. As I mentioned before, a charged species will dissolve much more easily in water than a species that has no charge. One way to test if a compound is an amine is to add an acid and see if it will dissolve in water. Quaternary ammonium hydroxides react with mineral acids to form quaternary ammonium salts. This hydroxide here will make this compound very basic. If you add a typical mineral acid such as HCl, this will react with the hydroxide to form water, and the ammonium salt that will be formed has a chloride ion, as the anion paired with the ammonium cation.